Our next topic will be a review of sinusoidal waveforms. In addition to that, I've also put up 13 trig identities that we'll be using throughout the steady state sinusoidal portion of our course. And we'll talk about when we will be applying at least a few of them today. So let's start with a simple sinusoidal function. I could express this sinusoidal function mathematically as x of t is equal to x naught cosine omega t plus some angle phi. And we're going to talk about what all of the parts of the cosine of this sinusoidal function are. Let's start with x naught. X naught is the amplitude or magnitude of the sinusoidal function. So that means that it is the distance that the peak value has in reference to the x-axis. So the peak value is exactly x naught units above our reference of 0, and this peak down here is exactly negative x naught units away. So we are able to quantify the amplitude of our sinusoidal signal by purely looking at the peak value of the signal. And if it's a positive peak, it's the amplitude, and if it's a negative peak, it's the negative of the amplitude. Our next term that we're going to look at is omega, where omega is what's called the angular frequency. So a sine wave is a periodic function, meaning that for every cycle, there is a fixed time interval t that occurs between the top peak and then the positive peak of the next corresponding cycle. You may recall from your engineering 121 class that there is a relationship between this period and what's called the linear frequency. Okay? So that relationship is t, the period, is equal to 1 over f, where f is the linear frequency. The linear frequency is simply a measure of how many cycles per second occur. So it has units of cycles per second, which is commonly called a hertz. Well, the angular frequency is the angles per second. So we can get the angular frequency by multiplying we can get the angular frequency by multiplying the linear frequency by a factor of 2 pi, because there is 2 pi radians per cycle multiplied by cycles per seconds gives us the angles per second. 1 divided by 2 pi. I'm sorry, I'm messing things up here. So we have F is equal, no, that's not right. Omega, is equal to 2 pi f measured in radians per second, again because there are 2 pi radians per cycle times the cycles per seconds gives us radian per second. And then we can substitute this relationship in. So if omega is equal to 2 pi f, then t is equal to 2 pi over omega. So this is our relationship that relates the angular frequency to that time period t. So this is just telling us how quickly this signal is oscillating. Now this last bit over here, phi, is what's called the phase angle. And this is the part that's probably the most confusing for students, maybe because you haven't dealt with them an awful lot. I've drawn this particular sinusoidal signal such that the peak value does not occur at t is equal to 0, which is what we would expect for a cosine function, and the zero crossing where it is increasing does not occur at t is equal to 0, which is what we would expect for a sine function. Instead, there is some offset or time shift that is happening. So our phase angle is simply a measure of that time shift, either left or right, where if phi is positive, our waveform x of t is shifted to the left, and this is important. It may seem counterintuitive, but I'll explain it in a minute. By t is equal to, so the amount that it shifted by phi divided by omega. So that is an angle in radians divided by something in radians per second. So we have radians per second gives us time in seconds. Now, the reason why it shifted to the left for positive values of phi is because that means that we are happening at an earlier point in time, okay? So the more to the left we are shifted, the larger the positive phase angle will be, because we're happening earlier and earlier and earlier than we would expect. If phi is negative, our waveform x of t is shifted to the right by an amount t is equal to phi over omega. So this is the role that our phase angle plays. It's just a measure of how much we are time shifting our waveform to the left or to the right, and it's related to the angular frequency. All right, so one thing that we're going to be doing an awful lot of in our circuit analysis course is comparing sinusoidal waveforms. And to do that, we need to follow some very specific rules. And we'll detail those rules right now. So rules for sinusoidal comparison. The first rule is that all waveforms need to be expressed exclusively as sine or cosine functions. So if I have a signal x of t is equal to 3 cosine 30t plus 10 degrees. And I have a signal y of t is equal to 2 sine 30t minus 20 degrees. I can't actually compare these two until I express x of t in terms of a sine function or y of t in terms of a cosine function. Typically in electrical engineering, we deal almost exclusively with expressing all of our waveforms as cosine functions. So I can use trig identity number 1 to change my sine function to a cosine function. So trig identity number 1 says sine of x is equal to cosine of x minus 90 degrees. So all I'll do here, my magnitude's going to stay the same, so I'm going to have 2 cosine, my angular frequency and all that stuff is going to stay the same, but I need to subtract 90 degrees from my original phase angle. So negative 20 minus 90 is negative 110 degrees, and I'm now in a place where I can compare these two sinusoidal functions. Rule 2 is that all waveforms need to be expressed with positive magnitudes. So I might have a signal z of t is negative 5 cosine 30t minus 45 degrees. And I could use trig identity number 4 to express that as a cosine function with a positive magnitude. And I do that by shifting my phase angle by plus or minus 180 degrees. So that would be 5 cosine 30t. And if I shift my phase angle by positive 180 degrees, negative 45 plus positive 180 gives me positive 135 degrees. And now I could compare z of t to x of t if I so chose. The last rule is that all waveforms need to have the same frequency. Now, there is no trig identity that's going to allow me to change the angular frequency or the linear frequency of a sinusoidal function. So it either matches it. Notice that I've expressed all of these with an angular frequency of 30t. They could all be expressed with a linear frequency of 30 divided by 2 pi, whatever number that comes out to be. But they would the frequencies would match for all of our different sinusoidal functions. So again, there's no trig identity that you're going to find on this list or anywhere, to my knowledge, where you could manipulate the frequency of a sinusoidal function. So these are our 3 rules for comparing sinusoids. Now let's talk specifically about that comparison. And the most common comparison that we are going to be doing is called determining leading or lagging. And this is actually a little bit of a confusing topic. All right. So I'm going to graph very roughly those 3 sinusoidal functions. I'm going to use different colors for each one. So let's start off with x of t. I'll do that in blue. It is time shifted by 10 degrees, a positive 10, which means it's going to be time shifted slightly to the left. It has a magnitude of 3. So let me 1, 2, 3, 4, 5. That's going to be, let's see. Alrighty, so it's a cosine function, which means that 0 should occur at t is equal to 0, but instead it's going to occur slightly before t is equal to 0 because of that time shift. So I'm going to put that there, which means the 0 crossing is going to be here, that 0 crossing is going to be there. That's not right. So very roughly, my blue curve is going to be x of t, where it's a sinusoidal function, time shifted slightly to the left. Y of t is a cosine function with an angle of negative 110 degrees, so it's going to be time shifted to the right. So if this were pi over 2, which would be 90 degrees, then my peak value of 2 should be occurring somewhere around here, which means my 0 should be there. This. So it's going to look something like this. And lastly, we're going to have z of t, and it's time shifted 135 degrees. So that's going to be, this would be 180, so smack in the middle here. It's going to have a peak of 5. Alrighty, so this is z of t. So this is a very busy looking graph, okay? And I, with a PhD in this stuff, actually struggle with interpreting graphs like this. So what we could do, let's go through the fundamentals and the basics of things first, okay? So we can say that z of t is leading x of t. Our green curve is leading our blue curve because the positive peak of the green curve occurs in time earlier than the blue curve. And it's going to lead by the difference of the angles. So 135 minus 10 degrees. So z of t is leading x of t by 125 degrees. We see that by observing that the green peak occurs earlier in time than the blue peak. Okay. So let's write this down just so that we can see what's happening. (135 minus 10 is 125 degrees. Alternatively, and this is just a different way of looking at things, we could say that the blue curve, x of t, is lagging z of t by that same amount because this peak occurs in time later. All right. If we wanted to look at what's going on in the purple curve, for instance, we can see that these two peaks are very far away from each other. So those aren't the ones that we should be looking at. Ideally, we would look at the peaks that are closest to each other. So if we wanted to look at this guy and this guy to get a comparison between y of t and z of t, we could see that y of t is leading z of t because the peak value occurs earlier in time. And it's going to lead. So here we have negative 110 degrees, and this is positive 135, but that positive 135 corresponds to this bit. So we're going to need to subtract 360 from it to get this peak. So 135 minus 360 is negative 225. So we have negative 110 minus negative 225 gives us an angle of positive 115 degrees. And this is why I say this stuff can get very confusing very quickly. We could again also express z of t as lagging y of t by that same 115 degrees. And if we wanted to, we could compare x of t and y of t as well. But let's introduce, in my opinion, a much easier method of making these comparisons, which is what's called the phase diagram. So, I guess I should have left, let's see, blue was x of t, I believe. Purple was y of t. And green was z of t. So, a phase diagram, let's start there. It's a simple plot where over here is 0 degrees, and then this is 90 degrees because there's a right angle between these two. This is plus or minus 180 degrees. And then down here would be negative 90 degrees, or positive 270 degrees if we wanted to go all the way around the circle. All right, so in a phase diagram, what we are doing is we are taking a snapshot of these sinusoidal functions at t is equal to 0, okay? So at t is equal to 0, we have 3 times cosine of 10 degrees. So I have a magnitude of 3 and an angle of 10 degrees, so that's going to be something like this. So this is x of t, and this is the angle, positive 10 degrees. For y of t, we have 2 with an angle of negative 110 degrees. So negative 110 would be around here. And finally, z of t is 5 with an angle of 135 degrees. So 135 is going to be this guy. There we go. So there are 3 different signals, x, y, and z of t, and we're looking at them at the snapshot at t is equal to 0. So if I want to know by how much z of t leads y of t, what I do is I start measuring from y of t in a counterclockwise fashion. Counterclockwise gives me leading, clockwise gives me lagging. So if I want to know how z of t leads or lags y of t or x of t, I start measuring at x of t, and if I want the leading value, I go this way. If I want the lagging value, I go this way. So z of t leads x of t by 135 minus 10 degrees, because x of t is 10 degrees offset and the z of t is 135. Or we could say that z of t lags x of t by 10 plus 180 plus 180 minus 135. So by 125 degrees, which is exactly what we saw earlier, or z of t lags x of t by, again, so we're going to start from here. We have 10 degrees to get to our horizontal axis, 180 degrees to get to our negative horizontal axis, and then to that we're going to add this small bit right here, which is 180 minus 35, and we get 300 Sorry, 180 minus 135. That's what the issue is. Excuse me, 235 degrees. And these two numbers should add up to 360. So in my mind, using the graphical method like this, the phase diagram makes things extraordinarily easy. Usually at this point, I have students just call out different things and we will figure them out. So let's just arbitrarily say we want to know at what angle does y of t lag z of t, okay? So if we want to know by what angle y of t lags z of t, we start at z of t and we're going to start measuring clockwise. So here's z of t. So this is the angle that we're looking for, okay? So we have 135 degrees from here to here. And then we have 110 more degrees. So that is going to give me 245 degrees. It's that easy. Y of t lags z of t by that amount. So we start measuring from z of t where our angle is getting more and more positive the further we go around our circle. If we want to know at what angle does x of t lead y of t, get rid of this guy because we're doing another measurement. So y of t is our reference, and because we are measuring leading, we need to be measuring counterclockwise. So we start here, and we're measuring from the purple to the blue, like so. So it's going to be 110 degrees, because that gets us back to our 0 axis, and then 10 more degrees, 120 degrees. So hopefully this is fairly straightforward. One thing that I would like to point out, when you're doing your homework problems that regard determining whether an angle is leading or lagging. This method works 100% of the time. But WebWork cannot interpret, say, that 0 degrees is the same as 360 degrees, is the same as 720 degrees, etc. So if you follow this methodology and WebWork is telling you that you got the wrong answer, add 360 degrees and resubmit. And if that doesn't give you the right one, subtract 360 degrees and resubmit. One of those three, and again, they all represent the exact same angle, will definitely be the correct answer. It's just WebWork isn't smart enough to be able to make that decision. All right, that's enough for our sinusoidal review. Thanks for watching.